The next thing we'd like to talk about is Descartes' rule of signs. To narrow the list of possible rational zeros, we can use Descartes' rule of signs, which will list the possible number of positive and negative real zeros. Note that the real zeros include both rational and irrational. Not just the ones from our possible rational zeros list, but also the irrational numbers. Now, when would you want to use Descartes' rule of signs? Let's say you have a list of maybe 16 possible rational zeros, and you're like, oh, I don't really feel like doing every single one of those to find one that works. This will take that finite number, might be a large number like 16 possible zeros, and it can narrow it down and maybe help you choose either maybe just the positives or start with the negatives, or once you find a positive, then you can stop looking for more positives or something like that. Descartes' rule of signs will not tell you what the zeros are. It'll just take that list of possible rational zeros and narrow it down. Fortunately, to find the number of positive real zeros, not that that will find the positive zero, but to find the number of positive real zeros is not too bad. We are going to count the number of sign changes between each of the terms of f of x. And we will know that the number of positive real zeros is equal to the number of sign changes of f of x, or less an even integer. Even integers because the complex come in pairs. Also, irrationals come in pairs, and so that's why we subtract off an even integer. So let's talk about what is a sign change of f of x. Well, let's look at the first term. The first term is positive x to the fourth, and the next term is negative 6x cubed. So from the first term to the next visible term, we have going from a positive to a negative, and that's what we call a sign change. We're just going to use SC for sign change. From negative 6x cubed plus to positive 22x squared, we have another sign change. We change from negative to positive, so that's going to be a sign change. From positive 22 to negative 30 coefficients, again we have another sign change. And from negative 30x to positive 13, we have a sign change, which tells us that we have 4 sign changes of f of x. That means that we will have a possible 4 positive real zeros, or less an even integer. So I'm going to subtract 2, and that's going to get me 4 minus 2 is 2 positive real zeros. And let's subtract 2 again. 2 minus 2 is 0 positive real zeros. So I might have 4, or I might have 2, or I might have 0 positive real zeros. So if I'm picking, this might not actually help me too much about narrowing it down. It says I might have a lot of positives. Let's take a look at how to find the number. Again, the number, not the actual zeros, but the number of negative zeros. To find the number of negative zeros, we're going to find f of negative x. Now, we found that in previous sections so that we could use it now. So we're going to actually find f of negative x and count the number of sign changes of f of negative x. This is going to take us slightly longer than the last one because we have to actually evaluate f of negative x. Step 2 says the number of negative real zeros is equal to the number of sign changes of f of negative x, or less an even integer. Okay, so I have the same function, but this time I want to know the number of negative real zeros, so I'm going to evaluate f at negative x. Negative x to the fourth minus 6 times negative x cubed plus 22 times negative x squared minus 30 times negative x plus 13. simplifies to positive x to the fourth, because a negative times a negative times a negative times a negative, 4 negatives turn out to be a positive. When I cube negative x, I get negative x cubed times a negative 6 is a positive x cubed. Squaring negative x, I get positive 22x squared. Negative times a negative is a positive 30x plus 13. And now that I have evaluated f at negative x, I'm going to count the number of sign changes of f of negative x. Well, I'm going from positive to positive, that's not a sign change. Positive to positive, that's not a sign change. Positive to positive, nope. There's no sign changes. And you might be thinking, well, that was a bust. That doesn't give me any information. But it does. It gives you a very powerful piece of information. Because I have no sign changes, or 0 sign changes, that means I will have 0 negative real zeros. That is a very powerful piece of information, because when I have my list of plus or minus this possible 0, plus or minus this possible rational 0, plus or minus, I am not going to try any negative real zeros at all. I'm only going to be trying positive real zeros, or in this case positive rational zeros, because I know that none of them can be negative. So this actually is a very helpful piece of information for this problem, because it cuts my list in half. I won't try any negatives because it's not going to work. And that's what Descartes' rule of sign tells us. So next we're going to try an example of just using Descartes' rule of signs to find out the number of positive or negative real roots. Then we'll take it and put it together with all the rest of our steps. We are asked to use Descartes' rule of signs to find the possible number of positive or negative real zeros. So to find the positive real zeros, I'm just going to look at the sign changes of f of x. Looks like I have one sign change from the first to the second term, another sign change from the second to the third, and then another sign change. That tells me I have 3 sign changes of f of x, which is going to give me 3 or 1 positive real zeros. To find the possible number of negative real roots, I'm going to have to evaluate f at negative x. Negative x cubed is still negative x cubed times negative 2 is positive 2x cubed. Negative x squared turns into positive plus x plus 7. And it looks like I have again 0 sign changes of f of negative x. And this is going to tell me that I have 0 negative real zeros, which will tell me if I'm looking for the actual zeros or the actual roots of the function, I'm not going to choose any negative zeros to synthetically divide because none of them will work. I will only try positive. Now some students might say at this point, well, if there's no negative real zeros, how come there could be 1 or there could be 3? And the reason is because Descartes' rule of signs only talks about real roots. It does not say anything about complex. So we could have 3 positive real zeros, and that would take all of the zeros that we needed. Or I could have 1 positive real zero and then 2 complex. Remember, the complex always comes in pairs, so that would be the 2 options I have. I know I'm not going to have any negative, so I wouldn't even bother trying. One thing to note at this point is Descartes' rule of signs is an optional rule. You don't have to use it, but it may cut down your time when you're trying to find the actual zeros. And we may be using it on the next couple of examples to narrow our list. The next example says find all your zeros and graph. So we're putting together the last several sections and putting it into one big picture. And this is really what the last couple of sections have all been leading up to, being able to find your zeros and graphing them. And this is where it's all at. My degree here is 3. My leading coefficient is 1. Notice that 3 is odd and 1 is positive, meaning that my end behavioral will be down, up. Because I have a degree of 3, I'm looking for 3 total zeros, whether they're real or complex. Next step says to find the possible rational zeros, which means I have to look for the factors of 10 over the factors of 1, which are plus or minus 1 times 10 in the numerator, or 2 times 5 in the numerator. The denominator, the only factors of 1 are plus or minus 1. So my possible rational zeros are plus or minus 1, plus or minus 10, plus or minus 2, and plus or minus 5. Those could be in any order. I have a list of 8 total possible rational zeros. So I could be doing this 8 different times. Well, instead of doing that, let's take a look at Descartes' rule of science to see if I could take this list of 8 possible rational zeros and maybe I can knock them down a little bit. So notice that f of x has no sign changes. Positive to positive, positive to positive, positive to positive. There are no sign changes, which tells me that I have 0 positive real roots or zeros. No sign changes means I have no positive real roots. That didn't take me any time at all. Because I have no positive real roots, I'm only going to be trying the negatives. In fact, I'm not even going to find f of negative x to find the number of negatives because that information is not going to be real helpful to me. It's either going to have 3 or 1, but that's not really going to be all that helpful to me. So I'm just going to take only the negative ones. So I have negative 1, negative 10, negative 2, or negative 5 that I'm going to pick from. And usually at this point in the class, I let someone just call out one of those 4 numbers. I don't really care which one it is. I'm being pretty lazy here. I just usually start with the smallest one because I'm really hoping that my numbers don't get too big. So I always just start with the smallest one. You can start with whichever one you want. So I'm going to drop the 1. 1 times negative 1 is negative 1. Add down. Multiply negative 11. Add down. And I was lucky. Alright, so I got a 0. I got a remainder of 0. Because I have a remainder of 0, that tells me that this negative 1 is in fact a 0, which happens to be negative. We told you that there wasn't any positive anyway, so I can rewrite this f of x as x plus 1 from the 0. If negative 1 is 0, x plus 1 has to be the factor, and then my remaining polynomial, which is now quadratic. Yay, and I don't have to do any more guesswork because once you get the remaining polynomial to be quadratic, then you can just factor if you can or use quadratic formula. In this case, it factors. Lucky us here. This is x plus 1 and x plus 10. So I have the factored form of the polynomial. X plus 1, I'm going to write squared because we have 2 of those factors. Now I can find the zeros. The zeros are negative 1, multiplicity of 2, and negative 10. Remember, if you have the zeros, then you better get your x-intercepts right, because the x-intercepts are just your zeros written in a point form. So negative 1 comma 0 and negative 10 comma 0. To find your y-intercept, we're evaluating f of 0, so I'm going to go ahead and use the original polynomial. I always like to use the original just in case I made any mistakes along the way. So we have 0 cubed plus 12 times 0, which is 0, plus 21 times 0, well that's 0, plus 10. I really like the evaluating at 0 here, especially when it's written out in general form, because it's really just that constant term. 0 plus 0 plus 0 plus 10 is 10. So that's my y-intercept. Now I'm going to use this information, the x and y-intercepts, with the end behavior to graph. And then we're putting all of the puzzle pieces together from the last several sections. My x-intercepts are negative 1 and negative 10. My y-intercept happens to be at positive 10. And I know that my end behavior is down, up. At negative 10, I have a multiplicity of 1, so it goes right through at negative 10. At some point, I have to turn around because I'm going to have to hit negative 1. I don't know exactly where it turns around, but that's okay for this class. Notice that negative 1 has a multiplicity of 2. And when we have a multiplicity of 2, our graph touches the 0 and turns around. Which helps us because we have a y-intercept at 10, so we're going to have to come up here, hit the y-intercept, make that a bigger dot there, and then we're going to keep going up towards infinity. Notice that my multiplicity, meaning the bounce, and matched up with my end behavior. They kind of go hand in hand there.